I'm Johan Malmqvist, in case you don't know me before, the Vice Director of the area of Advance, and have the honor of introducing the talk of today. Just a few words about the seminar series. Why do we have that? And the purpose is to share some knowledge of a general kind, let our researchers speak about their labs or their research in general, or so forth, in order to stimulate some discussions, stimulate some co-use of equipment, maybe stimulate some collaborations even, but also get an overview of what else is going on at Chalmers in production for those who take part. And it's been working quite well so far, I think, and we have a good program for today as well, of course. So we've learned about what we're doing in composites, about the Stena Industrial Lab, about what we're doing in circular economy, in data-driven design, and so forth. And today we are going to learn a little bit more about the one of the very most popular concepts at the moment, that is of digital twins. So everyone speaks about digital twins, although maybe with a little bit different definitions of what that really means. And what we're going to hear is Rikard Söderberg's take on this topic, and that is in the context of his and his group's work on variation simulation and robust design. So this is an area where Rikard has been working in since 1989. So he is a recognized world leader in the domain. And in addition, his work has been extensively applied in industry for solving these kind of problems. So I'm very much looking forward to Rikard's talk today, to hear about digital twins for geometry assurance in individualized production. Please, Rikard, the Zoom window is yours.
Okay, thank you very much, Johan, for this nice introduction. Yes, as Johan said, have been in this area that I will be talking about today for many years. I'm professor here at IMS, Industrial Material Science, where I'm also head of department. I'm also director of Incvis Laboratory, chairman of the board for Fraunhofer Chalmers Center. And my research since many years back is geometry assurance, robust design. So I still have a research group, fairly large one, around between 15 and 20 people in this area. I'm also the founder of RD&T Technology, which has been around for over 20 years. So I will focus today on digital twins for geometry assurance in individualized production. And I will basically divide this talk into a little introduction on digital twins, what we mean and what we mean in my area, then go into variation simulation as we use it in the design phase and has been doing for many years, go over to how we can use variation simulation in the production phase, basically as a digital twin. So that is the outline of the presentation. So if we start a little bit about what is the context, what is the situation right now, we as applied researchers, we are working very close with industry. And as we know, there's always a forced competition about quality, increasing factory throughput, flexibility, both when it comes to products and production systems, individualization and sustainability. So there are a lot of requirements and a lot of competition in these areas. If we look on the subject of digital twins, we see that we have been doing working with computer support, CAD systems, different type of simulation support and so on since the 80s now. And we can see that a lot of the optimization algorithms are getting faster. We get increased computer power, increased amount of available data. This is something we've been talking a lot about the last years, that we think there will be a lot of data available for almost everything in the future. and also increased connectivity. So systems are able to talk to each other in real time. So this makes us see that we can use simulation, basically, that we have been using in product development and production system development phases, in early phases, but use them to control production systems in real time. If we can feed the simulation models with real-time data, maybe we can use the simulation models to control and optimize production systems or parts of the production system. And if we can do that fast and in real time, we can also maybe move from mass production to more individualized production, where we're able to change things depending on what's coming into the system. So that's why we are saying towards digital twins. This is still some work to do. We working with simulation is always about accuracy and speed. And speed is, of course, important when we talk about digital twins and doing things in real time. But this is the situation where we are now. If we then go on a little, often when we say that we have a digital product description, that digital product description is often nominal. So if we have CAD models, these are always nominal. These are perfect. These are what we want. In reality, however, in all our production processes, manufacturing processes, we have variation. It means that we don't get the nominal product out of the system. We get variation. So this variation comes from part manufacturing, stamping, forging, whatever we do to create parts. We also add variation when we assemble parts together. We may add variation from joining, for instance, welding or spot welding. We apply heat and force and we deform the parts. And we end up to the right in this figure with some variation in the final product that may not look good, may not be okay from a customer point of view. So if we want to have a real digital twin or digital twins, actually you can develop a digital twin for a certain purpose. So it could be to describe the product, or it could be to describe a production system. But in order to get it as close to reality as possible, we need to include variation from the manufacturing system. So for us, this is something, variation is something, as I said, we've been working with for many, many years. And generally, you could say that all manufacturing processes has variation. So when we do things, it's not exactly the same from one part to another, from one action to another. We get a little variation depending on precision in machines or precision in operators and so on. So if we manufacture individual parts, we get variation in the form and the size of the parts. And when we assemble them, we also add variation to this process. So basically, it could be that we are violating or not fulfilling requirements on assembly level. This means that maybe we cannot put the parts together. They don't fit. Then we need to do something, rework or scrap the parts, and there is a cost and often a delay related to these types of problems. It could be also that we are able to assemble, but something is not perfect with the function. If the product is sold to the customer and this is discovered, we can read about it in the papers, and we need to send the product back, and there's a lot of cost related to that, and bad publicity, of course, for the company with this problem. There are also problems related to what we call perceived quality. If we think that the product looks good or not. So typically in the automotive industry, the relation between all the parts, we call them split lines. If we have nice gaps, equally sized and not too big, we think it's looking good, and we think it's a high quality product. If they are different and not parallel and so on, we think it's a low quality product. But all this comes from variation. So, and actually the industrial or engineering way to handle variation is to define tolerances. How much variation can we allow and still secure assembly function, and it looks nice. And so this is really the key to mass production, because in mass production we say we want interchangeability among parts. So if I have a number of parts, they should fit together. I don't make one part to fit to another part. So this started actually in France with related to some firearms mechanisms some 100 years ago, but we often say that mass production related to automotive industry in the beginning of in this case it's from 1913, a picture from the Ford assembly line. Well, this is where we started actually with mass production in large scale. So and the situation still after 100 years of doing this is that the tighter the tolerances, the less variation you can allow, the higher the cost. So of course there is a large interest from industry to try to make to control this variation and to make also the products insensitive to variation. So that's why we still work with this. So we also use the word geometry assurance to actually describe the set of activities that together aims to minimize the effect of geometrical variation in the final product. So it's not only one action or one activities, it's some activities. But of course, in early design phases, we have a specification of the product. We need to break those overall product requirements down. For us, it ends up with tolerances and locators for individual parts and sub-assemblies, because that's how the overall geometrical requirements on the product are broken down into requirements on the part level. So most companies do this in some way. It ends up with tolerances on the drawing or a CAD model. In pre-production, before we go into production, we need to decide what to inspect and how much and so on, because inspection is expensive, and the more information we can get from our inspection activities with less inspection, the better. So we cannot inspect everything. We need to inspect as little as possible, but get as much information as possible. During production, typically we inspect, we use the data to do analysis, to fix problems in ongoing production, but also to give feedback to design. A lot of the companies we are working with and the products we are working with are refined in cycles. So every 7 years, there's a new product family, new platform with variants of a product, for instance, if it's a car, for instance. But if we use basically the same concept, basically the same machine, basically the same suppliers, we can actually get some knowledge from this production phase and use it in the next design phase to calculate for that variation. So most companies do this in one or another way. Some do it by simulation, digital tools. Some still do it a lot manually. In our research group, we have since we started in '97, developed simulation software, RD&T, robust design and tolerancing, that is a toolbox for minimizing the effect of geometrical variation. So we have a number of functions that can assist in this loop to make the product robust, to do variation simulation, see if we meet the requirements, to do joining simulation optimization, to do inspection preparation, and to also use inspection data in production to control production. And this is what I will come to, that what we call the digital twin, when we use simulation in production to actually improve quality based on inspection data. So I will come back to that. So to simplify our area a little, we can say that there are basically two parameters that we are dealing with. If we start on the bottom, it's the variation itself. So as we said, all manufacturing processes have some variation, and the less variation you can allow, the higher the cost. So the less variation, the higher precision in the machines, the more expensive machines, the more maybe control you need to put in. So the other area is the robustness. If you can make the concept insensitive to variation, then of course you can allow more variation and you still deliver the functionality and the looks of the product that you want. For us, the robustness in a physical system like this is controlled by where we put the what we call the locators or the contact points between different parts. So typically a product is made up of a number of parts. The contact between the parts, this is where the variation propagates from one part to another. So if I can optimize where the contacts between the parts are, I can also reduce the effect of variation, reduce the variation propagation in the system. So we have a lot of optimization routines to do that. So if we go into then, how can we use simulation in the design phase? If we start there, basically what we have been doing for many years now. So as we say here in the design phase, this is before we go into production. So typically we don't have the production data, but we still want to do simulations. So what we do is we use historical data. Of course, we use inspection data or production data from similar processes to do some estimations or simulations that are fairly good. So what do we then do? We have, if we start in very early phases, we can optimize the concept of a product without knowing all the details about variation in the individual processes. So what we do is here we have an analysis that we call stability analysis, which is basically a robustness analysis. And this is to optimize the locating scheme. The position of the contacts between the parts, as I said, was important for the robustness. So normally, if I position a part like this rear lamp, I position it towards the body. So I have a contact between the lamp and the body in some points. There could be small pins or small planes and holes and so on. The red arrows are the symbols that describes where those contacts are. So if I put the contacts like this between the two parts, and I put the unit disturbance in all these points, I can see how that affects the geometry of this rear lamp. So in this case, I have in the red area 9.46. It means that if I have a 1 millimeter disturbance in those red arrows, the contacts between those two parts, I get almost 10 times amplification in this red area, which is not good. If I do a variation simulation, we are using Monte Carlo simulation here, and then I put the real tolerances on all the parts, and I run a number of thousands of Monte Carlo iterations. And if I, for instance, want to see the variation between the rear window, the glass, and the rear lamp, I can do this Monte Carlo simulation, and I get, in this case, with the tolerances and the locating scheme I have here, 8.92 millimeters. And this is not so good. We see we have a capability index, which should be like 1.33 or above 1.64. So, but this is far too low. Okay, so what we can do is we can change the position of the locators. So if I, for instance, change this locator to an area here by moving it, in a simulation, the color coding is upgraded, and we can see now everything is blue. So I don't amplify variation anymore. If I do a Monte Carlo simulation with the same tolerances, I haven't tightened any tolerances. I've just moved one contact point. We're down to 3.3 millimeters. So almost 2/3 of the variation is reduced by just moving this contact point. And this is, of course, something we can do in very early phases when we are still in the CAD system. We are working with digital models. We cannot do it when we have the tooling stamping tools ready, because then it's too expensive. Where we can play around with this in the early concept phases to find the best position of the locators, to reduce the need for tight tolerances. And as I said, so this is the first step. The next step then is to put the real tolerances on. And as I said, if you do that and run Monte Carlo simulation, you can get the value. How much variation do we get in the critical dimension? And typically for a company like Volvo here, they have a number of critical dimensions and a number of scenarios that they want to analyze to see, do we meet the requirements with the locators that we have and with the tolerances that we have on the parts. We can also color code the variation. So instead of looking at the distribution in one area, I can color code the whole variation in a relation like this. So if these are two parts put in a fixture with these red contact points describing how these two parts are fixed in the fixture, and I want to weld here, then maybe it's good to see how much variation do I have between the parts where I'm supposed to weld. Is it okay, or will my weld gun, my weld robot, will it miss the geometry totally because I have too much variation? So that's another scenario. Then we have something we call contribution analysis, which is basically, as it sounds, what are the main contributors to variation? So if I have a critical dimension here between the glass and the lamp, I want to analyze that. There could be a large number of underlying parts that builds up to this variation, and I need to see who is the most responsible for the total variation. If I need to tighten something, it's not obvious because we have a statistical analysis and we have 3D effects with a lot of rotations. We can also have second order effects where parameters play together. So then we have this analysis where you can see that in this case, 57.7% of the variation comes from a certain tolerance on a certain part. So if I want to reduce variation and don't need to think about cost, I just take the one that contributes the most. If I need to think about cost, I can also relate costs to these tolerances and do a tolerance cost optimization. So these are this is the main functionality that we use. And as we have seen, if I go back, this is how the visualization is done in RD&T. If we put all the glossary and environments and everything on, normally engineers don't work in that mode. It may look like this or this, but you can put all these things on, reflection, shadow, and environments and everything to make it look more realistic. We also have interfaces with other visualization software. So the intent is that management in early phase can see, if I have this concept with those tolerances, those locators, and so on, I can get something like this or something like this. Is this okay? Then we go on. If it's not okay, we need to do something. So this is a help for decision making in early phases. We also have, when I said that we can play with the locators to make it more robust. If we assume rigid parts, which is valid for some cases, we have basically 6 degrees of freedom, and we often lock those 6 degrees of freedom with 6 points. But if I have sheet metal parts or plastic parts, they typically bend and deform during assembly. If they are not perfect and they are put in a fixture, clamped together, they will bend. So we also have a built-in finite element solver in the software where we can then handle all these over-constrained locating schemes where we basically have more than 6 degrees of freedom, or we add a number of clamps that makes the parts bend when we put them together. So then we use finite element meshes as representatives for the geometries. We can apply as many clamps and spot welds also. So these are spot welds. This is a little more complicated case from a real company we are working with. We have something we call contact modeling, which is an automatic contact detection. So if the parts are penetrating each other in the digital world due to the variation, we need to detect that and bring them together and have a force equilibrium, because they cannot penetrate each other in reality. So that adds a non-linear effect to this assembly modeling, which makes it a little more complicated. But we can do it for, as I said, for non-rigid variation, non-rigid parts also. So these are the basic simulation capabilities we are working with. If we then go into the production phase, we can see how can we use this type of simulation to control variation if we have real-time data. So we have a large project called Smart Assembly 4.0 that we have been running for almost 5 years now, a lot of people involved. What we said in that project when we started was, what if, because everybody said there will be a lot of data available in the future. So we asked ourselves, in our area, what could we do if we had scan data on all the individual parts in the future? Because there are a lot of companies working with fast scanning, accurate scanning. So it means that basically you can scan all the parts that comes out from a process, and you can maybe also keep some type of identity, so you can relate the scan data to an individual part, and suddenly you know everything about the individuals. Normally you don't measure that much, you just measure a little, and you don't keep track on the individuals. But if you could keep track on the individuals, what could you do then? So typically in a cell like this, where I put two parts together, I have, so this is the cell, I have some robots working together. I have locators, which is the fixture here, clamps that clamps the parts, and I have a sequence. I weld in a certain sequence. So if I say I have two parts coming in, the yellow part and the green part, if I can scan the parts, maybe I can do some sorting, and maybe I can adjust some things in this cell to reduce the variation out. So we have been working with 3 principles. First one is selective assembly. The other one is locator trimming. And the third one is weld sequence optimization. And I will say some things about those techniques. So if we go to the first one, which is called selective assembly. A selective assembly has been around for many, many years, started already in the 50s. The idea is that you sort parts into groups. You measure them and you sort them into groups, depending on their dimensional outcome. And then you match the groups together. And by doing that, you can reduce variation. So instead of randomly position parts to each other, you group the parts, and then you combine the groups in a way that gives you lower variation out. So this is possible to do with groups when you work with rigid parts, when you have typically one dimension on the part affecting another dimension on the assembly level. When we work with non-rigid parts that are flexible and bend, like sheet metals and plastic parts, it's not so easy to group the parts, because we don't know what would be the grouping criteria, because everything bends. So what we have been doing is that we see that we need to do individual matching. So if I have 10 parts of each, I need to run them towards each other and see what is the best combination. And this is, of course, a quite time-consuming simulation that you need to do. We need to run the non-rigid simulation, including finite element analysis, contact modeling, and everything. So we've been working a lot with this, finding optimization methods, mostly based on genetic algorithms that can now pretty fast find the best combination of parts to reduce the variation out. So this is quite a promising technique that we see. The other one, locator trimming, sometimes it's called shimming. It's done today manually in many industries. This is basically As I said, if these are the contact points with the fixture, this is how the part is put in the fixture, and you want to minimize the variation here between the two parts. Maybe you can adjust the fixture a little to compensate for the part errors. This is all because the part is not perfect. So if the part is not perfect, maybe you can adjust the fixture a little to change the position of the part. And this is, as I said, done manually today for batches. What we can do in the future is, if we have scan data on the parts, we can calculate in our system how much to compensate, how much to adjust the fixture to make the relation between the parts as good as possible. So we have made some demonstrator cases that we can run from RDNT. So basically, I get scan data from the two parts. I calculate how much to adjust the locators for each pair of parts coming in. So this is one technique. We did actually a first publication on this in 2003, but now when we think we can get more data from manufacturing, we think we can automate it and use it in a digital twin. The next or the last technique we are working with is the weld sequence optimization. So as an example here, I have two parts. They are not perfect. They are put in a fixture. I have 4 weld points. And if I have 4 weld points, I get 4 faculty, which is 24 different sequences. And maybe you can run all the 24 sequences. If you do that, you see there is one best sequence and one worst sequence. So, and there's quite a lot of difference between them. So here we have 2 parts, same fixture, same parts, same tolerances. One sequence gives this and one sequence gives this. So of course, there's a great potential in finding the best sequence, and then you can reduce variation without reducing any cost. You just change the sequence. It doesn't cost more for the robot to take this sequence than to take this sequence. But the problem is that in large assemblies, you have many more weld points. So if you have 10 spot welds, you have 10 faculty, which is 3.6 millions. And to run that with a simulation, that takes too much time. So we have been working also here with optimization algorithms, and we have some algorithms now that can find a good sequence in minutes. So we are coming close to the times we need to be able to run it in real time. So if I then look at the reduction, if we summarize those 3 techniques, we see that we have done a number of test cases. I don't show all of them, but so these are basically mean values of everything we have run. But if I apply selective assembly, this technique to combine parts, I can basically reduce variation in the total batch with 40%. If I use locator adjustment to adjust the fixture for the parts coming in, I can reduce variation with 60%. And with spot welding sequence, I can reduce variation with 30%. These are rough numbers. You cannot apply them all. So because the first method you use basically takes most of the potential reduction. And these are also potential reductions, because of course there is a cost related to applying them, whether you need to scan everything, you need to build fixtures that have this adjustable positioners, or you need to change the welding sequence for each pair. So of course there's a cost related to it. So you cannot say what to apply when, but it depends a little on how large the batches are, how expensive the parts are, and how easy it is to adjust things. But these are quite a good potential. So just show you how in our demonstrator how this works. So we have a number of parts here, we scan them, and we keep track on who is who. Before we do anything, if we would like to do selective assembly, we can calculate what is the best pairwise combination of the parts. The robot gets the instruction of what parts to take. And you see it's not one, it's another combination. We put it in the fixture, we clamp with some adjustments in the clamps or in the locators, and then we can also distribute the work between the robots. So it could be many robots sharing the workload. They take a number of points each. So then we need to find out what is the best combination, who does what. We end with scanning the assembly. And by scanning the assembly, we can see that we have a little difference between what we simulate and what we get in reality, because there are other sources of variation also that we are not able to include in the model, or we will not include in the model because it becomes too heavy. But then we can learn from this scanning. So you put everything together, and by doing this, you can reduce the variation in the output here a lot. As I said, now we showed all the techniques: selective assembly, adjusting the locators, and the sequence, but in reality you choose one of them. So in order to make this work, we have, of course, a lot of simulation algorithms. We are working with RDNT for variation simulation, with IPS for the robot planning. So if I do something from the geometric side, then the robot needs to change. So we need to have new programs for the robots. But this can be fairly easy updated. So depending on the parts coming in, we calculate something from a geometrical point of view, suggest something, and then the robots needs to follow. In this test implementation that we are using, we have an infrastructure. It's a case-based system with a case handler. It's modular, it's distributed. We use a Kafka message bus to send messages between all those entities. And we use the JSON format for the messages. So these are standard ways of communicating between. So in this case, it's all digital, but in reality, we see, of course, that this is just a digital copy of the real real production cell. And then, of course, we communicate with the real robots and the real fixture. So that ends my presentation. To summarize then, we see that we are reaching a point where we are able to use simulation in production as digital twins to increase efficiency and accuracy. We see that the algorithms and the computer power and the connectivity are there. We still need to work a little on the calculation times, but we can also see that it depends on where in our situation here, it depends on when you scan the parts. If you scan the parts when it leaves the supplier, maybe you have weeks before you need to put them together. So then you have weeks for the calculation. If you scan them seconds before you put them in the fixture, then of course it's less time. But this is something that we think we now can start to use. And as I said, in the design phase, we use stability analysis, variation simulation, and contribution analysis to optimize the system, the product, and the production system, and the fixtures. And already here we do a lot of optimization. So, but then if you apply those techniques, selective assembly, locator trimming, weld sequence optimization, we can reduce variation with more than 50%, depending on what we choose in production. So first we do a lot of optimization in the design phase, and then we can take a lot more also by doing this individualized adjustment in production. So we see a great potential here. So that concludes my talk, Johan.